All closing, it went to about 6 amps.
Hello, Paul. We've been having trouble maintaining a constant level in this clear well tank, and I've got the controller in manual right now to settle it out. Could you get someone to take a look at it for me?
Sure, Tom, we'll take a look at it. Will, the operator just called and said they can't maintain a clear well level on automatic. Could you go out and take a look at it for me?
Sure, I can do that right now.
Let's see. That system's kind of complicated. I better take a copy of the system diagram. I might need it. It's been a while since I've worked on that system. I think that tank's located down in the basement.
The technician is going to check on a problem with one of the clear well tanks located on a lower floor in the plant. His knowledge of pneumatic instrumentation and his ability to read and understand system diagrams will help him solve the problem. In this unit, we're going to use an example of a level control system to discuss pneumatic instrumentation, basic pneumatic instrument groups, and their functions. We'll also talk about symbols that are commonly used to represent these instruments on plant system diagrams. These diagrams will prove to be invaluable to you in diagnosing and correcting problems in the instrument systems found in your plant. Pneumatic instrumentation. The word pneumatic means worked or moved by air pressure. These pneumatic instruments use air pressure to work or function. In many plants, pneumatic instruments play an important role in the overall operation of the plant. These instruments are used to measure, indicate, record, and control process variables like temperature, flow, and level. Let's take a minute and discuss the basic components generally found in a typical plant's pneumatic compressed air system. We know that pneumatic means moved or worked by air pressure, but where do we get this air pressure? The first component typically found in an air pressure system is an air compressor. An air compressor functions to increase the pressure of air by taking in atmospheric air and squeezing or compressing it into a small space. This increases the energy of the air so that it can be used by various equipment in the plant. The compressed air flows from the air compressor to the next component in the flow path, typically a moisture separator. Because atmospheric air contains moisture, it's necessary to remove as much of this moisture as possible to prevent rust and scale buildup in the system. A moisture separator functions to remove most of the moisture suspended in the compressed air. But often, other contaminants, such as lint, particles of dirt, and smoke, remain in the air. We'll discuss how these contaminants are removed in a minute. From the moisture separator, the compressed air flows into a receiver. A receiver is essentially a storage tank for compressed air. It provides a large volume of compressed air for the many uses found in the plant. The air can be removed from the tank in a steady stream and can meet any momentary change in demands on the system. We initially removed some of the moisture and contaminants from the compressed air by using a moisture separator. However, moisture and contaminants still remain in the air. Components referred to as dryers are used to remove some of the moisture and contaminants in the air by using either a refrigeration condensing process or a moisture-absorbing chemical. Either of these act to further filter and dehumidify the air. Often the next component in the flow path is a pressure regulator. A pressure regulator functions to maintain a constant pressure. The amount of pressure is determined by the requirements of the plant and plant design. Typically, most plant station air systems operate at pressures in the range of 100 to 180 psi. The components we've discussed so far function together to provide a constant, relatively dry, compressed air. These components make up what is often referred to as the station air system. The station air system provides compressed air to operate, for example, pneumatic tools, sandblasting, and cleaning equipment. It also supplies air to the second air system we'll talk about, the instrument air system. The instrument air system provides the power source for the operation of pneumatic instruments found at various locations in the plant. Because of the sophisticated mechanisms found in these instruments, the air flowing to these instruments must be cleaner and drier than the air in the station air system. For this reason, an instrument air system often uses additional dryers to remove essentially all of the remaining moisture and contaminants in the air. This air flows from the dryers into additional regulators that reduce the air to an acceptable designed pressure for the efficient use by the pneumatic instruments in the system. Many instruments in the system operate at different pressures. For this reason, regulators are often located near an instrument to assure the proper pressure for the design of that particular instrument. In the next segment, we'll see how compressed air is also used to transmit signals. These pneumatic signals carry information that represents specific plant conditions and are referred to as control air. Briefly stated, control air is a pneumatic signal that indicates and controls varying plant conditions. But we'll discuss control air in greater detail when we look at the different groups of basic pneumatic instruments. Before we go on to the next part of the program, we'd like to mention that the number and types of components used in a compressed air system may vary from plant to plant depending on plant design. Check with your instructor for the layout of your plant system. But for now, read the material in your text and ask your instructor any questions you may have. In the last segment, we discussed the function of components that generally make up station air and instrument air systems, and how these systems provide compressed air as the energy source for the operation of pneumatic tools and instruments found in the plant. In this part of the program, we're going to discuss the basic groups of pneumatic instruments commonly found in instrument systems. We'll use a simple diagram to show how these instrument groups function together to control a common plant condition, such as the level in a tank. In addition, we'll discuss a type of air pressure, control air, that is used for transmitting signals indicating various plant conditions. When discussing the manufacturing operation of any plant, you'll usually be talking about how materials and substances are changed or modified in the production of a final product. Commonly, the changes these substances go through from start to finish are referred to as the process. As instrument technicians, you'll be concerned about the measurement and control of the physical conditions of the process that vary, such as temperature, pressure, flow, and level. These physical conditions are commonly referred to as process variables. This is an example of a pneumatic instrument control system that monitors and controls a process variable, such as the level of liquid in this tank. This pump, which is a component in a circulating water system, is used to maintain constant flow to the tank and other parts of the plant. This valve functions to control the amount of liquid flowing from the pump to the tank. By controlling this liquid, the valve maintains a required level in the tank for the efficient operation of the system. Let's look at the different types or groups of instruments commonly found in an instrument control system and see how they function to ensure the proper operation of this valve. The first instrument group we'll discuss is designed to monitor a process variable, which in this case is the level in the tank. This device is referred to as a transmitter. A transmitter uses instrument air as the energy supply source to produce a pneumatic signal that indicates the condition of the level in the tank. A transmitter responds to a change in a process variable by using a sensing mechanism to convert the change in the process to a standardized signal called control air. It's called control air because it's used to operate additional instruments that control, or in other words, monitor and maintain the desired value of a process variable. The standardized signal is proportional to any change in the process variable. By standardized, I mean that the signal falls within a range commonly used in pneumatic control systems. By far, the most common range is 3 to 15 psi. For the tank in our example, 3 psi would indicate an empty tank. 15 psi would indicate a full tank. Other examples of variables that can be monitored are flow, temperature, and pressure. For a visual indication of any change in level in our example, pneumatic systems often use indicators. Indicators are a group of instruments that use control air to operate a mechanical device, such as a gauge, that produces a visual indication of the process variable it monitors. Indicators can be located near the transmitter or at other locations. For this reason, they are commonly referred to as either local or remote indicators. Another group of instruments in this system are recorders. Recorders are devices that not only visually indicate the condition of the process variable, but also maintain a constant record of the process variable. Recorders continually mark or record the condition of the process variable on a chart. Operators and technicians use this chart to see how the system has been operating over a period of time. Often there are additional instruments associated with a system that provide several different functions. For example, several types of these instruments that you may be familiar with are alarms, pressure switches, or meters. Even though these are different types of instruments, they have one function in common. They provide some type of indication of the process condition. Generally, these instruments receive information in the form of one quantity and convert it to information in either the same quantity or a different quantity. For instance, they can convert a pressure signal into a pneumatic or voltage signal. An example of one of these instruments is the level alarm on the diagram. Should the level in the tank increase or decrease beyond a required limit, the alarm will both visually and audibly alert system operators of the adverse conditions in the tank. To regulate a controlled variable, pneumatic systems use another type of instrument called a controller. A controller is a device that operates automatically by comparing the incoming signal from the transmitter to a predetermined set point. The set point in this case is the desired level in the tank. The controller computes any difference between the set point and the incoming signal and sends a corrective pneumatic signal to the remaining components in the system. From the controller, the signal travels to a control station. Control stations are a group of instruments that allow an operator to select either automatic or manual control of a given process variable. For example, should an operator feel that conditions warrant manual rather than automatic control, an operator can switch the control from automatic to manual. In the automatic control position, the signal from the controller travels through the control station and to the next instrument in the system. The final control element. The final control element is a device that regulates the value of the process variable. In this system example, the final control element is a control valve that's receiving a signal from a controller regulating flow to the tank. Let's take a minute to look at the overall operation of this system in an automatic control situation. If for some reason the level in the tank begins to drop below the desired level, the transmitter produces a signal indicating a decrease in level. This signal will cause the indicator and recorder to reflect the change in level, and if level drops below a required limit, an alarm will sound in the control room. As the controller receives the signal from the transmitter, it operates automatically to produce a signal that opens the control valve. This increases the flow of liquid to the tank and returns the level to normal. We used a very simple diagram to discuss the basic groups of pneumatic instruments commonly found in many plants. However, in an actual plant, pneumatic instrument systems are usually more complex. For this reason, plants rely on plant system diagrams to show the layout of these systems and the components found in them. In the next part of the program, we'll discuss how these basic instrument groups are represented on plant system diagrams. But for now, read your text and answer the questions. Be sure to discuss any questions you have on the pneumatic instrument groups used in your plant with your instructor before you go on. So far, we've discussed pneumatic instrument groups and how these groups function together in a typical instrument control system. In this segment, we'll look at how these instrument control systems are symbolized on plant system diagrams. We use this simple diagram to discuss the various types of instruments found in a typical level control system. But realistically, an actual plant diagram looks like this. Now, this diagram may seem complex, but with proper knowledge of the symbols representing the different components and instruments, this diagram should not be as difficult to read or understand as it may appear. A plant diagram is a very useful tool. As a technician, you'll often use this tool when troubleshooting and diagnosing system malfunctions. Simply stated, plant system diagrams give the layout of components and instruments in a particular system and show their relationship to the operation of that system. The first step in understanding how to read plant system diagrams is to learn the symbols that represent the various instruments and components in the system. These symbols are located on a legend. A legend is simply a list explaining the meanings of the symbols found on the diagram. When reading any plant diagram, it's important that you use the legend to familiarize yourself with the symbols for the types of components found in the system. For our discussion of pneumatic instrument systems and diagrams, we'll use the symbols recognized by the Instrument Society of America. Now, some of the symbols may vary from the symbols used on your plant diagrams. You should check with your instructor for any variations of the symbols used in your plant. Let's concentrate on the level control system that we looked at earlier and identify the pneumatic instruments with their symbols. The power source for pneumatic instruments is compressed air. As you know, the compressed air system consists of several components. To simplify the diagram, this symbol will represent a compressed air system. The pneumatic tubing that connects compressed air systems to various instruments is symbolized by a line with hash marks. But instrument systems commonly contain electronic instruments as well. An electronic signal path is represented by a line like this one. We mention this because when reading plant system diagrams, the lines connecting components will indicate the type of component or instrument you're dealing with. Okay, let's look at the first instrument group on this diagram, the transmitter. The standard symbol for any instrument is a circle containing letters which indicate the function of that particular instrument. For example, this is the symbol for the level transmitter that we discussed earlier. So its symbol is a circle containing letters that indicate its function. The meanings of these letters will be located in the legend on an identification chart. Let's take a minute and look at a simplified version of an identification chart. Along the left-hand column, you'll find letters from A to Z. Each of these letters have corresponding meanings to the letters in the symbol. For example, this instrument is a level transmitter. The first letter in the symbol designates the process variable. Using the chart, we find the letter L and we see that it indicates level. The succeeding letter in the symbol is used to designate the readout function. The letter T, in this case, indicates a transmitter. We'll discuss the other information in this symbol later. The level transmitter produces a pneumatic signal which is connected to the remaining components by pneumatic lines represented by this symbol. This symbol represents a level indicator. The first letter, L, represents level. Using the legend, we find that the succeeding letter in the symbol, which is an I, represents an indication function. So the letter symbol LI represents level indicator. As we stated earlier, indicators located near the transmitter are referred to as local indicators. Remote indicators, located elsewhere in the plant, are distinguished by a line drawn through the symbol. A level recorder is symbolized like this, LR. L represents level, and the R represents a recording function. Therefore, LR is the symbol for level recorder. Similarly, this instrument, which is a level alarm, is represented by the symbol containing the letters LA. So far, the instrument symbols have been fairly easy. The two letters in the symbol represented the type of instrument and its function. But what if an instrument has more than one function, like this level indicating controller? To symbolize an instrument with more than one function, the symbol may contain more than two letters. In this case, the first letter is L for level. Its readout function is I for indication, and according to the chart, the letter C for its output function is control. So you can see that the level indicating controller is symbolized LIC to designate its functions. The level control station is symbolized by the letters L and K. Again, L means level. The K, as seen on the chart, represents a control station function. So we now know that this symbol means this component is a level control station. The last instrument in our level control system, the final control element, is a valve that controls flow to the tank. By regulating the flow, the level in the tank is maintained at the proper level. In this system, the final control element is specifically referred to as a level control valve. As you can see, it is symbolized by the letters LCV. In addition to the letters that identify the type of instrument and its function, other information is often included in the symbol. In plants that have many similar systems, the individual systems and their instruments are identified by placing numbers and letters within the instrument symbol. For example, suppose this plant had 4 systems, similar to this level control system. To identify this particular system from the other systems, the symbols contain the number 1. If the system is relatively complex, then additional information may be found in the symbol. For example, the number 1 that identifies the system may be followed by a letter or possibly a number that further identifies a particular instrument. This information can assist a technician in locating and identifying the instrument in a fairly complex system. You'll notice on this diagram there are other components, such as the pump and valve. In the next part of the program, we'll discuss other symbols used on plant systems diagrams that represent mechanical components found in most plants. For the types of instruments used in your plant, it's important that you use the legend on plant diagrams to identify the symbols and to find out other information about the instruments. So before you go on to the next part of this program, be sure to clear up any questions about information found on plant diagrams, and don't forget to read the text and answer the questions. In the last segment, we looked at some of the symbols that represent pneumatic instruments. You may have noticed that there were mechanical devices other than the pneumatic instruments illustrated in this system. In this segment, we're going to look at some of the symbols for mechanical devices found on various plant system diagrams. The most common type of plant system diagram is referred to as a P&ID, or piping and instrumentation diagram. These diagrams provide information that applies to the design and layout of an entire system. Due to the complexity of some plant systems, individual portions of a system that control a particular process variable, such as level, are contained on a diagram commonly called a loop diagram. In this simplified loop diagram of a level control system, this pump functions to move liquid to the tank and other parts of the system. Even though there are many different types of pumps, this symbol can be used to represent the pump in this system. To maintain the level in the tank, the amount of liquid flowing through the system must be controlled. In this system, the final control element, which is a level control valve, functions to regulate the flow. In many process control systems, the final control element is usually a type of control valve. Because these valves are commonly used, let's briefly look at two types of these valves. One of the most commonly used valves is a gate valve. A gate valve operates by moving a disc or gate in the open or closed direction to either start or stop flow through the valve. A gate valve in a normally open position is symbolized like this. The symbol is modified when the gate valve is in a normally closed position. Gate valves are usually used only for starting or stopping flow. They are not used to control or change flow through a system. The next type of control valve we'll discuss is a globe valve. The disc in this valve moves in an up and down motion to regulate or stop flow through the valve. This is the symbol for a globe valve in a normally open position. And this is the symbol for a normally closed globe valve. Remember, there are many variations of these types of valves. The symbols we showed you are commonly used to represent them on plant system diagrams. To operate these valves, devices referred to as actuators are used to change valve positioning, or in other words, move the disc in the open or closed direction. Actuators are usually powered or driven by one of three means. The power sources are either pneumatic, electric, or manual. As you may recall, in our level control system diagram, the controller produced a pneumatic signal that caused the pneumatically driven actuator to open or close the level control valve. Let's take a minute and see how this works. If for some reason the level in this tank began to increase, the controller would produce a signal that would increase the pressure on the actuator. This would cause the stem of the valve to move the disc in the closed direction. Flow to the tank would be reduced and the level would decrease back to normal. If this type of pneumatic valve actuator is shown on a P&ID, it would be symbolized like this. Commonly, valve actuators have an additional instrument mechanism referred to as a valve positioner. The function of a valve positioner is to make certain that the valve moves to the correct position dictated by the controller. For example, if the signal from the controller tells the valve to move in the closed direction, but the valve sticks, or it remains in the open position, the positioner increases pressure on the actuator until the valve moves to the proper position. Valves with positioners are symbolized by adding a rectangle to the pneumatic actuator symbol. This is the symbol for electric motor actuated valves. These actuators use electric motors as the driving force for opening or closing the valve. A manually actuated valve can be symbolized with this addition to indicate a hand wheel. The hand wheel is used to manually open or close the valve. We've only discussed two types of mechanical devices found on P and IDs, but often there are numerous devices and symbols on these diagrams. For example, this symbol often represents heat exchangers or coolers. You may see this symbol used to represent a flow element, or this symbol used to represent a turbine. But remember, the best way to learn this information is to use the legends on the diagrams to familiarize yourself with the components and instruments in your plant's system. In the next part of the program, we'll discuss some other types of information found on diagrams that will assist you in understanding the layout of any system. But for now, read the material in the text and answer the questions before you go on to the next part. So far, we've been discussing the various pneumatic instrument groups, their functions, and the symbols commonly used on P and IDs to represent these instruments. We also looked at symbols that represent some of the mechanical devices found on P and IDs. In this segment, we'll look at a P and ID and discuss other important information on the diagram that will assist you in troubleshooting and maintaining the systems found in your plant. A P and ID shows the layout of various interrelated systems, but it also provides other useful information about the systems. Let's take a closer look at a P and ID and see what information is available. Titles of diagrams describe the overall function of a particular loop or system. This enables you to find the correct diagram when troubleshooting a system. The title of this plant's diagram tells us that we're looking at a flow diagram of the condensate lines. So we know that information for instrumentation in the condensate system can be found on this diagram. If you had to locate and repair an instrument in the condensate system, you'd use this print to find the instrument in the plant. Let's look at some additional information found on this diagram. For instance, this particular diagram has a legend. Legends are usually found at the beginning of a set of diagrams for the systems of a particular plant. But often, an individual diagram contains an additional legend with symbols of specific instruments pertaining to that system. The instruments and major components of a system are usually numbered to assist plant personnel in identifying the instruments in the field. For example, suppose a work order requested you to check an instrument on one specific pump in a system that utilizes two pumps. For identification purposes, these pumps could be numbered 2A or 2B. This enables a technician to locate the instrument he needs to check. To show how instruments and other components function and interrelate, the diagram shows process and control lines. As a technician, these lines enable you to look at the entire system and see how one instrument or component affects the operations of another. These lines indicate main process piping, or electrical and pneumatic control signals. These lines provide useful information when troubleshooting a system. Due to the complexity of many modern plant systems, diagrams commonly contain references to supplemental records or diagrams. These records or diagrams contain additional information pertaining to that system. For example, this diagram indicates that additional information on components connected to this system can be found on diagram 9862 FM 35A. Here we see additional reference drawings that provide information concerning other related components and systems. Often, plants modify a system to include additional components and instruments. This is usually the result of system modification to improve control of the overall system or a particular loop. For this reason, diagrams are constantly updated to indicate any modifications or additions to the system. As you can tell from our discussion, there's some very useful information found on system diagrams. Other information, such as calibration data, control logic, and fail-safe information, is often available. Your plant system diagrams may include additional information. In the next part of this program, we'll follow a technician as he uses some of the information found on a P&ID to troubleshoot a problem in an instrument control system. But for now, check with your instructor if you have any questions on information available on plant diagrams before we go on to the next part of the program. Now that we've discussed plant instrumentation diagrams and some of the information they provide, let's see how you can use this information as an instrument technician. In this segment, we're going to observe two technicians using plant system diagrams in their daily work. In the beginning of this unit, a technician was asked to troubleshoot a problem with a fluctuating level in a clear well water tank. Before going to the location of the tank, the technician examines the system print to familiarize himself with the instrumentation associated with that particular system. He's careful to look for interconnections within the system before beginning to inspect the individual instruments. He discussed the situation with the system operator to find out more about the problem and to make certain that the operator was aware that he would be working on that system.
The level is swinging when the system is on automatic, but in manual, the level settles out. As long as the system is in manual, I'll check the level transmitter first. The output's steady. Here's the supply line to the transmitter. I'll check the regulator to see if there's any moisture in it while I'm here. Some could have built up over a period of time. There's a little, but not enough to cause any problem. I'll take the cover off to see if anything is wrong inside. Everything looks alright. I'll check the output signal. Looks okay. Let's see. What's next? The controller. Well, the signal's not fluctuating. I better check inside to see if there's anything unusual. Looks fine. No linkage is off. But I'll use some leak detector while I'm here, just in case there's a leak in one of these lines. Squirt some here, a little over there. There's no bubbles here, no bubbles here either. I'll take a look at the print and see where the output of this controller goes. It goes to the level control valve. I'll just follow that line, see if there's any damage in the tubing. See, it comes out here, goes up there, across that beam, down this way. Here it is. Yeah, here's the control valve. This tubing looks alright. It's not bent or damaged. Supply to the positioner is okay. Signal from the controller is steady. The signal to the valve is alright. Everything looks okay. I wonder what the problem is. I think I'll call the operator and have him put the system on automatic, see how it responds. The controller signal is increasing, and the valve's moving. Uh-oh. Now the valve's closing. This valve is cycling. Now I know why the tank level is going up and down. Before I let this swing any longer, I'll get the system placed back on manual so it'll settle out and not cause more problems. I'll give Tom a call. Tom, the valve's swinging. Put it in manual. I'll check the positioner now. I'll get this cover off and take a look inside. Let's see. Everything looks all right. Nothing loose. I know if the linkage was off, it'd cause the valve to cycle. It looks okay. Let's see. What else could cause this valve to cycle? I better check my print. The signal from the controller and transmitter was steady when the system was on manual, but when it was on automatic, the valve started cycling, which I know has caused the level to go up and down. Something's keeping this positioner out of balance. I'll check the incoming signal. Squirt a little leak detector on the input bellows and see if there's a leak in here. Some all over. That ought to do it. There it is. A leak in the input bellows. This is what's keeping the positioner out of balance. It seems to be leaking between the bellows and the housing. It's probably just the O-ring. I'll get the operator to bypass this valve so I can remove the positioner and repair it.
In our troubleshooting example, the operator was able to control the tank level while the system was in manual. With the system in manual, the operator could apply whatever pressure was necessary to overcome the leak in the positioner and open the valve to a position that would settle out the level in the tank. But with the system in automatic, the leak in the positioner and the changing level in the tank caused the controller signal to cycle continuously. This caused the valve to open and close and the level in the tank to fluctuate. The technician used the system diagram to identify and check the components in the system. By using the diagram, he followed the signals from the components through the system. By using the information on the diagram, and with his knowledge of pneumatic control action, the technician was able to locate and repair the problem. Let's take a minute and see another situation in which a technician uses a system diagram. In this situation, the technician is modifying an existing instrument control system. The diagram provides the information needed to make the modifications and to install the instruments correctly. Another application for diagrams is when a new panel for a control system is being installed. The diagrams will have the correct information to install the instruments and make the proper connections. After completing the connections, the diagram also contains the information a technician needs to calibrate and check the operation of the instrument loop. What we've shown you in this unit is information that you as a technician will use on a daily basis. As you become familiar with the information contained on system diagrams, you'll see how it can simplify troubleshooting and maintaining efficient operation of your plant's instrumentation systems. Let's see how that level control system is coming along now that the technician has repaired the positioner.
Okay, it seems to be operating fine on automatic now. Now listen, while you're down there, would you mind checking out the flow transmitter for me on the DW makeup?
Plant system diagrams may appear to be difficult to read and understand at first, but the information needed to read and understand these systems is provided in the legend and on the diagram itself. As you learn to read the diagrams by using this information, your responsibilities as a technician will be easier to perform.